Hey everyone, and welcome. I'm excited to be here today to talk to you a little bit about how Electron works under the hood, and how we combine a series of other impactful projects to do that. Before I really get into it, though, let me take a moment to introduce myself. I'm Shelly, and I work full-time on the Electron project on behalf of GitHub, where I've been for about 2.5 years now. This work has also allowed me to explore and actively contribute to a pretty wide range of other open source projects and committees, including Node, Chromium, and TC39. I'm based in San Francisco at the moment, but my team's a distributed one, so I also manage to spend some time in places that are not San Francisco. Today, we're going to look towards answering a pretty broad but fundamental question. How do Electron's dependencies work together? And how do we use them to enable you to write the applications that you do? To try to get at a digestible answer to this question, we're going to hone in on a specific example of code using Electron's APIs, and then journey through its lifecycle from beginning to end. We'll stop every so often at steps along the way to draw attention to the dependencies at play so you can more clearly understand their roles. Some of you may be familiar with Electron, but for those who feel less familiar, I'll do a brief recap to make sure that we're all on the same page. Electron is a JavaScript framework for creating desktop applications with web technologies, like JavaScript, HTML, and CSS. It can be used on Windows, Mac, and Linux, as well as other platforms and architectures, like Windows on ARM and even Raspberry Pi. It works by integrating Chromium and Node, and then adding an extra layer of C++ and Objective-C code, which it uses to allow it to create fully formed GUIs, as well as take advantage of file system and networking capabilities with Node. Typically, desktop applications are written in the native system language for each platform, which means that you might have 3 different teams writing 3 versions of the same app. Electron enables you to write your app once and have it run on all applicable platforms. When we talk about dependencies that Electron has, what does that mean? You might be familiar with dependencies in a more prototypical JavaScript sense. They're, for example, what gets added to your Node modules folder when you run npm install inside of a project. Dependencies, at an actual definitional level, are basically just something your project needs in order to run. Electron has many little dependencies, as is often the nature of JavaScript-adjacent software. But there are 3, technically 4 players in Electron's dependency tree that really carry the team, which are V8, Node, Chromium, and a subcomponent of Chromium called Gin. We can discuss all these dependencies in the abstract, but I don't think that that'll really help us understand the interlocking mechanics of these dependencies in the clearest or most helpful way. Instead, let's consider how we can make this concrete. When you write code with the module in Electron, what happens under the hood? What dependencies are involved at each step? And what do they do? To paint this picture more clearly, let's jump out of the abstract and into some code. For today's purposes, I've chosen the dialog module, which Electron exports in order to allow you to create native dialogues across different platforms. Here, we can see a small snippet that carries out a single self-contained task. It creates an open dialog, allowing you, as the name suggests, to choose an item from your machine to open. We've specified that we only want to allow the user to open files with the open file property. So, more specifically, we're going to create an open dialog and then wait for the user to either choose a file or to cancel the dialog. Once they've taken either of these 2 pathways, the call resolves a promise with an object containing 2 items. A Boolean variable representing whether or not the user canceled the dialog, and then the user's file choice. If the user chose a file and didn't cancel the dialog, we then load that file into a browser window. On macOS, when we run this code snippet, we see this. That code snippet is comparatively few lines, but in fact, there's a full mountain of moving parts just under the surface of what might at first glance seem fairly straightforward. Let's dig in a little bit further and discuss what's happening in each different part of this snippet. We'll start with the overall flow of the code as it travels through Electron's file tree. Electron is primarily composed of 3 languages for its externally facing functionality: JavaScript, C++, and Objective-C. At its core, Electron doesn't remove the need for programs to be written in the platform-specific languages that they are. It just obfuscates those languages away from you so that you, as a developer, can focus on a single simplified API surface with JavaScript. Any given module is implemented along this spectrum, from JavaScript to C++ to Objective-C, depending on the needs of that specific module. Sometimes, whole methods will exist entirely in JavaScript. Sometimes they'll be sanitized or parsed in JavaScript and then passed to native implementations. And sometimes they'll be entirely native. In this case, we need access to platform-specific APIs. So we'll be starting out with some sanitization and parsing in JavaScript, and then implementing those methods natively with our primary API dialog files, which will then call out to different platform-specific functionality in 3 different subfiles. And now we come back to the code itself. Firstly, in order to access any of the methods on the dialog module, we need to gain access to Electron itself, which requires requiring the module. And with that, we've now arrived at our first big Electron dependency, Node. Node needs no real introduction. I mean, for better or worse, it's kind of why we're all here. Importantly, for Electron's purposes, this JavaScript runtime allows code execution outside of a browser. Principally, it allows Electron to access file system and networking capabilities. But for our journey today, it also allows Electron to create and export modules to users. Require can be used to import built-in modules, community modules, or local files. These files can be imported either with a relative path that will be resolved against the directory named by __dir name, if that's defined, or the current working directory. In our case, Electron is a community module, so that when we've installed it locally, Node will resolve it against the Node modules directory, where it can then be accessed. Now that we've required Electron and thus gained access to it, we can drill down a little bit further to access the dialog module. We can do this by destructuring the required Electron module, because the module itself is merely an object. All right, so now we've got the dialog object from Electron. Where are we going next? And how do we gain the ability to call methods on our dialog object? This happens, as it turns out, as a result of what's inside our top-level dialog JavaScript file, module.exports. Module.exports is a special object. It's what's returned as the result of a require call. Module is a variable that represents the current module, and exports is the object that will be exposed to represent that module in other files. So anything you want to export on a given module needs to be assigned to module.exports. Inside module.exports, we export the function that we've called on our original snippet, showOpenDialog. If we look at this exported implementation, we can see that it calls into another function called openDialog, and then passes along parameters alongside a new Boolean parameter, which determines whether or not we want to open this method asynchronously or synchronously. ShowOpenDialog is an asynchronous method, so we're going to pass false here to represent that. Inside openDialog, we do some parsing of arguments, like the openFile argument you saw in the original snippet. This might include whether or not we want to allow users to open files or directories, to show hidden files, or what to set as labels on different components of the dialog. After this parsing is complete, we come to this next most curious call, binding.showOpenDialog. This brings us to our next stage of implementation, bindings to C++ code. If we go and find the declaration for binding, we're confronted with another new and unfamiliar function, process.electronBinding. This is, in practice, what it might sound like, a binding of C++ code to JavaScript so that we can call into that native code from JavaScript. What is this thing, and how does it work? To understand how process.electronBinding works, we first need to look at Node's process.binding. Process.binding is a lower-level implementation of the require method, except that it allows users to require native code instead of other code written in JavaScript. For the first several years of Electron's life, we wrapped our custom Electron bindings with this lower-level variant. Process.binding wasn't really intended to be used by embedders, but as in many other things Electron's kind of done, we decided to do it anyway. This was fine for years, but it then bit us in Node v12 when it was released, because process.binding was actually removed from Node's internals following a deprecation period. And so any attempts to use it would error. And so we had to go and find a new, more embedder-friendly thing to use. First, we look towards process.internal binding, which is a binding type in Node that allows for accessing internal native modules that are not intended to be used by user code. It was added in Node v8.8.0 and maintains a separate cache and module list in order to avoid naming collisions. However, as you can see by the name, we quickly determined that this was not for us, and that attempting to use it would involve the sorts of nasty hacks and patches that we try to avoid as much as we can. Finally, we determined that the best way forward was an undocumented binding type called linked binding. This binding was far more geared towards embedders and allowed us to access native modules that were intended to be used by user code. This was also added in Node v8.8.0, and so we could migrate over to it with fairly little issue. And now back to process.electron binding. After determining that process linked binding was the node binding we needed to use in order to require our native code into our exported JavaScript code, we could rewrap our custom bindings. And so in the end, process.electron binding is essentially just a require call for C++ code with some extra Electron-specific functionality thrown in there to allow us access to stuff like performance statistics, handling of the event loop, and some other stuff like crash and hang handling. At this point, we've ended the strictly JavaScript portion of our code snippets lifecycle. We're now down into our first C++ file, which is where the functions that we've talked about binding actually live. I neglected to mention this earlier, but if you look at the file indicated by arrows, you might be a little bit confused as to why it's prefixed with atom_API. This is actually because Electron used to be called Atom Shell. We're slowly moving away from that nomenclature, but since a few files like this remain, any file you see that's prefixed with atom_API is actually just an API file in Electron with no relation to Atom. At the very bottom of this C++ file, we'll have the initialization function we actually use to create the binding. And this is where we first hit up directly against our next dependency, v8. Fewer of you are likely familiar with v8 than you are with Node, so we'll define it now. v8 is Google's open source, high-performance JavaScript and WebAssembly engine. It's written in C++, and it implements the ECMAScript specification. What this means is that it allows Electron to create JavaScript objects, promises, and other things you're familiar with in JavaScript, but in C++. So, as I've said, at the bottom of each of our native API files in Electron, you'll find a function called initialize. This function is identical in signature across Electron's different modules, and is integral in creating the native function bindings to JavaScript. In our initialization function, we can see a very important parameter, exports. This parameter is a v8 object, or the equivalent of a JavaScript object. This is where we'll be placing the functions that we've defined natively. We briefly need Node again here, as this initialization function is passed to some of Node's native registration components, where it's registered as a module. This does not, however, answer the question of where the function names and functions themselves get set. For this, we've arrived at our next dependency, gin. We class it as a dependency at the moment, given its role and its importance. But it is, in fact, a top-level project within Chromium's source tree, and is a set of utilities that make working with V8 easier. More specifically, in the context of Electron, it allows us to more easily marshal types between C++ and JavaScript. We initially forked this project under the name native mate in order to enhance its capabilities, and are actually right now in the middle of unforking this project and upstreaming our changes to Gin itself. As a result, any references in code you see to Gin helper are references to enhancements we've stacked on top of Gin's native capabilities. Now that we've discussed the role of native bindings, how do we create, set, and export the native implementation of show open dialog? The answer to this question lies with Gin's dictionary, which represents a key value store data structure backed by V8. It turns out that we can use a slightly enhanced Gin dictionary in order to write bindings for a function that either takes in an arbitrary JavaScript object as an argument or returns one as a result. This is perfect for our use case here. We want to create a simple JavaScript object containing a function that takes in parameters and then uses them to create a native open dialog. To do this, we can call a function called setMethod on the Gin dictionary in order to attach our native implementation of show open dialog to the underlying object for export. If you look to the slide, you'll see what this looks like in C++, both for our specific case with show open dialog, and then again for the generic case of any natively implemented method. And to make the effects of this more clear, we can also take a look at what the JavaScript equivalent of this is. As JavaScript developers largely, this is probably more immediately understandable. You can see the analogous example both for our specific case and then again for the generic case. And now, we've come a long way, and it's time to finally get to the native implementations themselves. What are we calling from the native binding that we're setting, and how does it work? If we recall back to the original code snippet, we know that this function resolves a promise after the user has made either their choice of file or canceled the dialog. We thus use Gin again here in order to create a V8 promise, which, as you could probably imagine, is equivalent to a JavaScript promise. We do that by using a typed helper class for creating promises natively, which we tell that we're going to give a type of Gin dictionary in order to resolve a JavaScript object. Finally, the bottom three files we've been seeing in this source tree as we've been through this presentation come into play. When we call file dialog : show open dialog on the second to last line of this function, what we're doing is that we're telling C++ that we want to invoke a function called show open dialog inside each of the three platform-specific files on the tree. I'll avoid delving too deeply into the platform-specific implementations, as they're a bit out of scope for our dependency focus here, but we can go over them pretty quickly. On Mac OS, we're going to want to use Apple's native NSOpenPanel APIs to create native dialogues, whereas on Linux, we're going to want to use GTK dialogues, and then finally on Windows, we're going to use iFileOpenDialog APIs. As we near the end of this function's lifecycle, let's now take a moment to talk about how we create the object that we know will be resolved in the promise returned by this function. It's similar across platforms, but for today, we're going to grab the macOS specific version. We told our promise that we'd be resolving with an enhanced Gin dictionary, but we still need to create and set values on that. We do that here. We create a new empty Gin dictionary and then take one of two conditional pathways. If the user canceled the dialog, then we're going to set a Boolean variable canceled to true and the file path result to empty. If they chose not to cancel, then we're going to set canceled to false and then fetch the paths selected by the user and then set them as the file path key. And this brings us a bit out of order to our final big dependency, Chromium. Chromium, which I've mentioned intermittently throughout this presentation, is an open source initiative developed by Google that backs the Google Chrome browser. It enables Electron to create fully formed GUIs. And so different parts of Electron hook into and depend on Chromium in order to do that. On the earlier slide, I mentioned that we resolve an array of file paths, which is shown on this slide as base : file path. This is actually an abstraction to isolate users from the differences between native path names on different platforms. We can take advantage of the work that Chromium has already done on this front in order to avoid needing to account for these differences across the different platforms that Electron supports. Finally, once we've populated the object with the fields that we want to resolve, we can call promise.resolve. As you'd expect, this resolves the promise for the user. And then, if they click the file, as you saw in the GIF, they'd see it pop up in their window, as we did. And with that, we're almost done. We've walked through Electron's JavaScript code as it intersects with Node.js, and then gone down into the underworld of C++, which has surprising impacts on JavaScript and the way that we use it to inform functionality in JavaScript. If you take anything away from this talk today, consider how much work goes into every aspect of the way that JavaScript works, and the energy and the brilliant engineering that so many people had to perform in order to make it happen as it does. Electron would be nothing without its dependencies and the people who build them. But we'd also be nothing without you, the community, who consume it and tell us how we can make it better every day. Thank you very much.